Okay, guys, this is chapter 9-2 for algebra. Please make sure you have watched the video for 9-1 before you watch this video. So, alright, so I want to teach you how to factor, and you're going to see this from now until you graduate college. You're going to need to know how to factor an expression. This is an expression because there's no equal sign. So we're not going to be able to find out what Q is, but factoring is the same thing that factoring means in regular, back in 6th grade. When I say factor 35, it just means turn it into its factors. Give me a multiplication problem that equals this. So this is essentially, this is like Jeopardy. This is your answer. We're going to take that and turn it into a multiplication problem. Well, to do so, what you need to do is take out the greatest common factor, which you learned in chapter 9-1. So, you can look at this expression, and I know from doing this for many years what the greatest common factor is. But if you don't know the greatest common factor in your head, if you don't know what goes into 10, and what also, the biggest number that also gets you 25 when you multiply, you can do what we did in 9-1 and do the prime factorization. The prime factorization of 10 is 5 times 2. So the prime factorization of 10q would be 2 times 5 times q. Then the prime factorization of negative 25q squared, remember we take out a negative 1 and 25, and then we have 5 times 5. So the prime factorization of negative 25q squared is negative 1 times 5 times 5 times q times q. And what you'll notice is, what do they have in common? They have one 5 in common, and they also have one of the q's in common. So the greatest common factor is 5q, 5 times q. So I'm going to take the 5q and bring it on the outside, because that's the greatest common factor. Now, what I'm going to do is essentially ask myself, if I'm taking out a 5q, well, what's left? Well, what you're essentially doing is you're dividing each of these by 5q. Well, if you have 10q and you take away 5q, you're left with 10 divided by 5, which is 2. Then over here, you're going to also divide by 5q. You have negative 25 divided by 5, which is a negative 5. And q squared divided by q, remember the rules of monomials, is just going to be 1q is left over. Now, this is the factored form. This is essentially a multiplication problem, because you have 5q times, this stands for one whole thing. This is one whole thing. This is one number. So it's this times this, which will lead you to get that original as your answer, 10q minus 25q squared. And if you don't believe me, if you just want to check it, go ahead and distribute the 5q back in. You will get the original answer, the original expression. But this is the factored form. Again, I knew that they each shared a 5 and a q before I did this, so you don't necessarily always have to do the prime factorization. This is what we learned how to do in 9-1. Alright, so the why are we factoring is going to come a little later. And I'm going to show you that later in the slide. But for now, you just have to practice factoring. So here's another. This is a binomial. This is an expression. There's no equal sign. So we're going to factor this by turning this into a multiplication problem. So I'm asking myself, what is it that they share? And this one has an a, and this one has two a's. This one has two b's. This one doesn't have a b. So the greatest common thing amongst them is an a. So when I divide each of these by a, I'm left with, well, here you end up with just one a on the top, so you have a b squared, and plus, well, you have a divided by a, which isn't 0, it's 1. And now, this is the factored form. This is the multiplication problem, a times this whole quantity, that will end up with that original problem. So what I've done is, remember, I've factored this, which means I've turned it into a multiplication problem that still gets you that expression. Let's try one more. Now, even though this is a trinomial, they still could have a greatest common factor. So from looking at the 4, the 16, and the 12, I know that each 4 goes into all of them. So the greatest common factor is 4, because I know 4 times 3 is 12, 4 times 4 is 16, and 4 times 1. So really, I know that 4 is going to be my common factor, but in case you didn't know, remember you could do the prime factorization of each of them. 2 and 2 is 4. 16, you get 4 and 4, and then 2 and 2. This, again, is what we learned in Chapter 9.1. And in 12, you get 4 and 3, 2 and 2. So when I line them all up, what you're going to find is what they have in common is each of them have 2 2's. So 2 times 2 is 4. Again, the greatest common factor is 4. Now, you also have to be careful with the variables. Look at the variables too to see what do they all have in common. And they each, even though this one has a b and this one has a b, this one does not. So it's not a greatest common factor. It has to be a factor of all of them. So the greatest common factor is 4a. Now, again, to find out what's left, I'm essentially dividing each of them by 4a. And when I divide each of them by 4a, for the first term, I'm left with ab squared. When I divide this one by 4a, you get 16 divided by 4. You get positive 4. The a's cancel out, b. And then when I divide this one by 4a, I'm left with just a positive 3. And this right here is the factored form. This doesn't look like a big multiplication problem, but remember it is. Because really what you're saying is 4a times all of this will get you that original problem, that original expression. So I've factored the expression, turned it into a multiplication problem. So now I want you to pause the video and try this one on your own. Now that you pause the video, let me show you what the answer would be. If you did the prime factorization of -8 and -12, you would have found that they each shared a negative. They each are negative, so they share a -1. And I know that 4 is the greatest common factor of both of them. So they each share a -4, and they have one a and one x. So the GCF is -4ax. Then I know that if I divide each of these by -4ax, you're going to have negative divided by negative. So you're ending up with a positive 2y plus 3, and then there's nothing else left. So this would be the factored form of that. And remember, the way that you can get very easily, if you can't think of the GCF off the top of your head, make sure you look at 9.1 and review how we can use prime factorization to get that. But remember, if you were to multiply this back in, you would end up at that original expression. But we wanted to do the opposite. We wanted to turn this into a multiplication problem. All right. So remember, factors, just a little review. I want you to pause the video and just see if you can say out loud what the answers to these questions. Okay. So now that you paused, for factors, you should have just said 2 numbers or 3 numbers that multiply to get to a bigger number. So like the factors of the number 40 could be things like 8 and 5, because those are numbers that multiply to get you 40. Prime factors are numbers that multiply to 40, but they're not 8 and 5. They're only the prime factors. So the prime factors of 40, I would do a prime factorization tree and break it down so I only got the prime factors. So the prime factors of something like 40 would be 2 times 2 times 2 times 5. Those are the prime numbers that multiply to 40. To factor something completely would mean essentially to break it into its prime factors. And to factor is to take a expression such as 3x squared plus 3 and take it and make it into a multiplication problem. So for this case, you would take out a 3 and you'd be left with x squared plus 1. And that's what it means to factor. Now we need to know why we're factoring. So there's 2 main concepts that you need to understand first before we talk about why we're actually factoring. Why are we turning something into a multiplication problem? The first thing is this. What's 5 times 0? Well, it's easy. It's 0. And what's 0 times -9? Again, it's 0. Well, how'd you know that? Well, if you multiply anything times 0, you're always going to end up with 0. Well, that's a concept in math called the zero product property. It's just a fancy way of saying that Well, if something equals 0 and you're multiplying two numbers, one of those numbers has to be 0. That's the only way your answer is going to be 0. So if I told you that a times b, the ab means a times b, equals 0, well, you don't really necessarily know what a is. A could be anything. B could be anything. But one of them has to actually be 0. In order for you to multiply these two numbers and get an answer of 0, let's say a was 100. Well, then b has to be 0. Let's say b was 1,000. Well, then a has to be 0. The only thing that you know is that if I told you that a times b equals 0, you know that either a has to equal 0 or b has to equal 0. Well, that works out in helping us solve things, because look at this problem right here. I know x plus 5, which I don't know what x is, but I know that this is all one term, and there's no sign here, so I know it's x plus 5 times x minus 7, and I know after you do the multiplication you get 0. Well, I don't know what x is, but I know if you're multiplying two numbers and you're getting 0, that means that either this whole thing has to end up being 0, or this whole thing has to end up being 0. Well, it's going to help us find out what x is, because if one of those has to be 0, I can just set each of them equal to 0. Well, x plus 5 has to equal 0. Now, I'm not saying x has to equal 0, but after you're done adding 5, it could equal 0. Or the other thing that would have to equal 0 would be x minus 7. Well, if you solve this algebraically, you could find out that if x is negative 5, or if you add 7 to both sides, x could actually be 7. And think about this. If you were to plug, remember x has to be the same in all one problem. So if you were to put a negative 5 in there and a negative 5 in there, yes, this one would not equal 0. That would actually equal negative 12. But negative 12 times, well, what would this one become? Negative 5 plus 5. Oh, 0. Well, what's negative 12 times 0? 0. Well, that's one way this answer could equal 0. Well, instead of putting in a negative 5, what if we put in a 7? So if I put in a 7 for this x, and I put in a 7 for this x, yes, 7 plus 5 is 12. That's fine, because over here, 7 minus 7 is 0. And when you take 12 times 0, you get 0. So that's using the zero product property. Now, and the other thing is to remember is that when you have a normal equation, you don't have to worry about factoring, because you all learned how to solve a problem like this. You add 9 to both sides and you get 2x equals, and then over here you get 22. You divide by 2 and you get x equals 11. So for problems like this, you don't need to know how to factor, but there's a reason, because in this problem you don't have a quadratic. This is just a normal equation. So now let's put those two things together and talk about this. A quadratic is when you have one of the variables to the second power. And if you have that, and I want to know what a is, I can't do this, because that is not how you can solve a problem if you have an a squared or a b squared or a c squared. So in here, I know that I can solve for a, and the difference is there's an equal sign. And now that I have an equation, I have to be able to solve this. Well, the way that you solve quadratics, one way that we solve, is by factoring. Because I know that this equals 0, if I could turn this into a multiplication problem, I'm going to have the zero product property. I'm going to be able to set both of them equal to 0 like I did here and here. Well, alright, so how do I factor? Well, we just learned this. If you have an a squared plus 3a, I can take out the greatest common factor, which in this case is an a. And if I take out an a, what's going to be left inside the parentheses is going to be a plus 3. Remember, that's how we divided each of these by a, and I'm left with a plus 3. Again, which equals 0. Well, look what you have now. You have turned this problem, this expression right here, into a multiplication problem. A times whatever you get when you do a plus 3. You get a multiplication problem. So you know that after you're done multiplying them, you end up getting 0. So now we're going to use the zero product property. Now that I have a multiplication problem that equals 0, I can say that either this has to equal 0 or this whole thing has to equal 0. So I'm going to set each of them equal to 0. A equals 0 and a plus 3 equals 0. Because one of them has to be 0. Well, there's nothing more to solve here. You get a equals 0. Here, I have to find out what a is, so I'm going to subtract 3 on both sides, and I get a equals negative 3. Well, now I found out a could either be 0 or it could also be negative 3. But a has to be one of those things, because otherwise, when you multiply these two things, it would not have equaled 0. So here are our two answers. Whenever you solve a quadratic, you're going to get two answers. Let's try another one. Here's a problem. Now, wait, hold on a second. Now, I did this to trick you. You already have a multiplication problem that equals 0. So you don't have to factor. This one is already factored for you. So this one's going to be quite easy. You'll see this from time to time. There's nothing you have to do. I don't want to multiply this x through. Because if I multiply this x and distribute, I get x squared plus 5x equals 0. Well, I can't solve this because I have a quadratic, and the only way you can solve this is by factoring. Well, now, I've already done this for you. It's x times x plus 5 equals 0. So I'm going to set each of those factors equal to 0. Here's one of my factors. Here's my other factor. And this one's already solved for you. And if I subtract 5 from both sides, I get the other answer, which would be negative 5. So x could either equal 0 or negative 5. It's got to be one of those. Try this one on your own. Pause the video, try it, and then watch. All right. So hopefully you noticed that it was a quadratic, so you can't solve it the normal way. You're going to have to factor it by doing the greatest common factor. So if I take out a 3, the greatest common factor should have been 3x. So inside, when I divide each of these by 3x, I'm left with x plus 3, which equals 0. So I factored it and equals 0. So now what I'm going to have to do is put my two factors, one of these, either that one or that factor, has to equal 0 in order for them, the products, to equal 0. So I'm going to set each one equal to 0. Solve both of them. You get 0. And by the way, one of the answers isn't always, in these problems they've been 0, but not all of them. It's not always one of them is 0. It's just so, it was just coincidence that each one of these, one of the answers was 0. So your two answers are 0, or you could also have a negative 3 as x. Last one. Well, here you might notice that you have to solve for x, and you have a quadratic, but it doesn't equal 0. So the first step in factoring is you need it to equal 0. So the very first thing I'm going to do is I'm going to move this 10x over to the other side by subtracting by 10x. And that gives us a problem, an expression that equals 0. So now I have 25x squared minus 10x is equal to 0. So let's factor this side, because the only way to find out what x is I can factor and use the zero product property. So the greatest common factor of negative 10 and 25 is a 5. And I'm left with, I'm sorry, and they each have, this one has 2 x's, this one has 1 x, so it's 5x. Here I am left with a 5x minus 2. And now I did my job. I factored the expression, so I have a multiplication problem. I've highlighted each of my two factors. 5x minus 2 is one whole factor because this stands for a number. And now I'm going to set each of my factors equal to 0 and solve for x. X equals 0, again, just a coincidence. And over here, I'm going to add 2 to both sides. And I get 5x equals 2, divide by 5. And I get x equal to 2/5, which is, you could leave it as a fraction, or you could have also said 4/10, 0.4. And there are your two answers.